coming. So today we have Hyunwoo Lee, who had an extensive travel recently to visit Princeton and Hamburg, and he came back, and then he will talk about random matchings and linear hypergraphs. Please.
Thanks for the introduction. I'm very happy to share my research with you. So, I think most of you will know what is the definition of the matching. The matching is just a collection of vertex disjoint edges in graph or in hypergraphs. So I think the matching is one of the most central objects in combinatorics. So there are many topics related to the matching, such as some graph embedding problems and design theory and extremal set theory, and also some other very many topics in combinatorics. And especially the finding a sufficient condition for the existence of a large or almost perfect matching or just a perfect matching are extensively studied in recent decades. So it is very natural to consider if there is some general result on the hypergraph such that it can guarantee the existence of the almost perfect matching. So I think this theorem provides some very nice and very general sufficient condition for the existence of the almost perfect matching, which is called the P-Pengel and P-Pengel-Spencer theorem. So it basically says that we have a K-uniform hypergraph, the same uniformity. If H is a K-uniform hypergraph, and also it is an almost regular, and it has a sufficiently small maximum codegree, then this theorem states that this hypergraph H contains an almost perfect matchings. So in particular, regular linear hypergraph contains
Can you remind us code degree?
yeah, the codegree. Okay. So just the degree in hypergraph is count the number of the edges instant with some fixed vertex v in here. The codegree is pair of, which is defined on the pair of vertices u and v. The codegree of u and v is the number of hyperedges that containing both u and v. And the maximum codegree is the maximum value of the codegrees. And this theorem states that when our hypergraph is almost regular, so for every vertex v, it insert with almost the same number of the edges, and the small maximum codegree, so every distinct pairs are contained in a small number of edges, then the given hypergraphs contains an almost perfect matchings. So in particular, regular and linear hypergraph contains an almost perfect matching. In here, the linear hypergraphs means that for any two distinct hyperedges, their intersection is at most 1. So obviously, the codegree of the linear hypergraph is bounded by at most 1. So it has a very small codegree. So by this P-Pengel-Spencer theorem, if the degree is sufficiently large, then regular linear hypergraphs contains a very large matching. Then one may ask that although most of the matchings in the regular linear hypergraphs are almost perfect, so to answer this question, maybe we can consider about the average size of the matchings in the given regular and linear hypergraphs. So to estimate the average size of the matchings in hypergraph, we may consider the random matching model. So let H is a hypergraph, and let N be a random matching which is chosen from the set of all matchings, which is chosen uniformly and random from the set of all matchings in H. Then the average size of the matchings in H is exactly the same as the expectation number of the size of this random matching. And to estimate the expectation of the random matching, we may analyze this to just a vertex by vertex. So what I mean is, for a vertex v, we may define event v bar, which I call v bar, which is an event that this random matching does not cover v. Then by the linearity of the expectation, we can estimate the size of random matching by summing up this the probability of this event, the V bar, for the order vertices, and we deduct it from the number of vertices of the H. Then we can get the average size of the random matchings. And I will define this notation pH, this type of definition x bar, y bar, and the condition known g bar, which means that this is the probability that the vertex x and y are not covered by a random matching M, which is conditioning on the events that the random matching also does not contain the vertex g. So if pH just an x bar means that probability of that the random matching does not cover a vertex x. And this is the conjecture of Kahn. It says that if a H is a deregular and linear K-graph, then for every V, he conjectured that pH V is almost the same to the value d to the minus 1 over k. So again, by the linearity of the expectation, if this conjecture is true, then the average size of the matchings in H is roughly 1 minus d to the minus 1 over k times n over k. If this conjecture is true. Okay, so to understand why Kahn conjecture this conjecture, I will explain why the number d to the minus 1 over k appears. Yeah, so why d to the minus 1 over k? So since our hypergraph is regular and linear, so for every distinct two vertices u and v, their incident edges are almost disjoint. Because the definition of the linear hypergraphs, their incident edges are there are at most one edges that can incident both u and v. So this linear hypergraph implies that the set of incident edges are almost disjoint. And also this is a regular, so heuristically we may assume that this value, the PV bar, is almost the same for every vertices V with some real number x. So we intuitively let's just assume that this PV bar is just an x for a V. And also by the linear definition of the linear hypergraphs, for distinct vertices V1 to the Vt, the events V1 bar to the Vt bar are mutually independent. We may assume, in some sense, almost mutually independent. Then now we fix vertex V and let E1 to the Ed be an edges that incident to V, and let's say EI is consonant with the V and U I1 to the U I comma k minus 1. This is a type of V, these are also V. Then this equality is hold. This means that the probability that the random matching does not cover V plus a random matching contains an edges E1 to the EI is just the whole event. Because the first term is the random matching does not cover V, not cover V. So to complete the equality to 1, the other term may estimate this random matching cover a vertex V. To cover a vertex V, it means that one of the edges in E1 to the ED, it must contain in M. But by the definition of the matching, these events are disjoint events. So we have this equality. And also we can estimate this probability, some edges contained in a random matching is exactly the same as the vertices that consisting this edge simultaneously does not contain in the random matching, because there is a bisection between these two events. If a random matching contains an EI, then we may remove this EI from the random matching, then it correspond to the events that it does not containing the vertices v to the v and u I comma 1 to the u I comma k minus 1, and also vice versa. So this equality is hold. So we have this in this equality. Now we will divide this formula by PV bar, then by the definition of the conditional probability, we have this equality there.
So can you go back? I mean, maybe I missed the explanation. So the can you explain? So the probability the EI is in M is equal to that. So the right hand side, is that the probability that none of these vertices are covered by matching?
The left hand side means
No,
that the
right hand side.
right hand side, yeah, the random matching does not contain all of these vertices v to the u I comma k minus 1. Because it does not cover this, then we just put on edge EI, then it is contained in the event that EI is contained in M. So there is a one-to-one correspondence between these events.
Oh, I see. So I know. Okay, so this is the hypergraph. Okay.
Yes, this is a hypergraph.
Okay.
So now we divided this formula by this number. Then by the definition of the conditional probability, we have this identity. Now we may, so this is just take the inverse of this formula. So now we may use the mutually independent conditions. So in some sense, just deleting, this probability means that conditioning on the event that V bar holds means that we choose a random matching from H minus V, because the random match conditioning on the event that the random match does not contain cover a vertex V means that just choose a random matching in the H minus V. So we can estimate this probability by this one, P H minus V to this number. And also H minus V is just deleting a one vertex from the in some sense large regular linear hypergraph. So in some sense this H minus V is still almost regular and still linear. So we may assume that these events are mutually independent. So we have this inequality. Equality. And our first assumption is the values PHV bar and these values PH minus VU IJ bar is almost same to some value X. So we finally have this equation. And d to the minus 1 over k is the unique positive solution of this equation. So this is why d to the minus 1 over k is conjectural value. Yeah, some bunch of calculations. But anyway, this is maybe this was the motivation of the conjectural value. And this conjecture was proved for the graph case by Kahn and Kim, the Jung and Kim. So it says that when G is n vertex and D regular graph and M is a random matching, then for every V, the PGV is roughly d to the minus 1 over 2. So the expectation of random matching is roughly the conjectural value. And also they provided the variance of the size of matchings. And their proof ideal is using the Godsil's identity on the matching polynomials and also analyze the random works on regular graphs. So they apply the martingale sequences on the random works on regular graphs by using Godsil's identity and combine something to prove this. And our result is we disprove the Kahn's conjecture for all k and list c. So yeah, let k is at least 3, and d0 and epsilon is just some positive real number. Then there is a d and d regular linear k uniform hypergraph H with the two vertices v1 and v2 such that the first one is the p v1 is greater than p v1 is almost 1, very close to 1, so very big. And p v2 is smaller than roughly 1 over d plus 1, so very close to 0. So two extremal cases. So this obviously disproves the Kahn's conjecture. Okay. And also we prove this theorem. Let H be K at least 3 K uniform linear hypergraph, and which is also D regular. Then this value PHV is lies between these two values, which is exactly same as these two values. So in some sense, these two probability values are best possible. So, okay. Now I will briefly explain how to prove these two theorems. So the basic idea is doing one step further than the previous heuristic calculations, the complicated calculations. So now let me define these two functions, g dx, which is 1 over 1 plus d minus 1 times x to the k minus 1, and fd is a composition of this function gd. Then it is just this number, this formula. And in the previous calculation, the heuristic calculation, we solved this equation. X is the g d plus 1 x. And so it means that if we build some tree-like structure, then the heuristic, the previous heuristic calculation will give x is this in some sense almost same as these many composited values. So in some sense, if we composite this the even numbers, then this is just x is same as the composition of this function fd. I mean, the tree-like structure in some sense can allow us to calculate some various number of good things to calculate it inductively. So yeah, I will explain it a bit later. Yeah, so why these things can be done, because once we do one more step further, then this gd plus 1x can be same as again gt plus 1x. So yeah, this type of things can be happen. So it is in some sense related to some convergence of the dynamical systems. So now I will compare the two cases when k is 2 and k is 3. So let k is 2 and d is 101 and y, and I will plot these two graphs. The blue one is the graph y equal x, and this yellow one is y equal fd to the x, where d is 101. And this value is 1 over 10, which is a conjectured value, 1 over d to the minus 1 over 2. Yeah, I mean d to the minus 1 over 2. So in some sense, almost 1 over square root of 101, which is very close to 0.1. So this is the conjectured value. So the basic intuition why the Kahn and Kim's theorem, the graph case, was true, because if we analyze this dynamical system, if we start with some value in here, then it approaches to this fixed point, and if we start to this value, then it approaches to this conjectural value. So in some sense, this dynamical system converges to the conjectural value. So this is the basic intuition why Kahn's conjecture is true for graph. But when k is 3 and if we plot the graph y equal fd to the x, the 1001, when d is 1001, then the shape of the the plot of the shape of the graphs are very different to when k is 2. It has a 3 intersection point with y equal x. So the first one is here, the middle one is roughly 0.1, which is the conjectured value, because since k is a 3, the conjectured value is d to the minus 1 over 3, so roughly 0.1. So roughly 0.1. But it has two other values, which is very close to 1 and also very close to 0 and very close to 1. But in this system, if we start with this point, it does not converge to this. If we start it here, then it goes to this value. And if we start at this point, then it approaches to this almost 0 point. So this is why we can disprove the conjecture for k and least 3. I mean, we can prove that when k is at least 3 and d is sufficiently large, all the graphs has this type of shapes. So our goal is construct a hyper tree-like regular structure inductively, I mean iteratively. So we can, so if this goal is success, then we can analyze the probability by using, in some sense, this type of graphs. So to this, I defined this notion D extendable K uniform hypergraph H. So, I mean, our goal is making a regular linear hypergraph which has a hypertree-like structure. So we may start with almost regular and define some operation on the graphs such that we can amplify this structure into inductively the hypertree-like structure. So the D-extendable linear hypergraph, the definition of the D-extendable hypergraph is as follows. We say that H is a D-extendable if all the vertices of H has degree D except one vertex V, which has a degree exactly D minus 1. And we say that this vertex V as the head of H and write it as a head H. And we can show that there are infinitely many sequences of D such that there is a D-extendable linear hypergraph. I mean, we can explicitly and inductively prove this lemma. So we can explicitly construct this D-extendable linear K graph. I will skip the proof of this lemma. So now we have the base linear hypergraphs. Now our task is define some suitable operation on this extendable hypergraph to amplifying this into a hypertree-like structure. So we start with the F, which is a D extendable linear K graph, and we define operation which I call SD. I will just drawing the definition. So basically this is like this. So we start with some disjoint copies of the extendable linear hypergraphs. This is the extendable, and these vertices are head of each hypergraphs. And now we introduce a new vertex V in here, and we will joining new hyper edges. So maybe we have exactly k minus 1 vertices in here, and each of these are disjoint union of the extendable linear hypergraphs, and these vertices are the head of the extendable linear hypergraphs. And we do these things exactly d minus 1 times. Then this vertex has a new hyperedge exactly 1, and it was the head of the extendable linear hypergraphs, so its degree became d. So d, 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 d. D, but this vertex has degree D minus 1. So this operation can amplify the extended linear hypergraph into the larger one. And this new vertex V is the new head of this graph. So this operation produces some other extended linear hypergraphs, so we can composite these operations. So this notion is well defined where SD0 is just F and SDLF is inductively amplifying this extendable hypergraph. Now let's analyze the equation x equal f dx. As the picture that in this picture we have exactly 3 solutions, and indeed there are exactly 3 solutions. So let's say gamma d, alpha d, and beta d are the solutions of the equation x equal f dx. Then we can easily show that gamma d is placed around in 1 over d plus 1, and alpha d is placed on the conjectured value d to the minus 1 over k, and beta d is very close to 1 minus 1 over d to the k minus 2. Then we can prove this lemma for substantially large D. There is a D extendable linear paragraph such that this value, the probability that the random matching does not contain this head when this amplified hypergraph is very, very close to the value beta D. When we composite this, we apply this operation in even time, then this probability is very close to beta D. And do it in odd time, then the probability is very close to the gamma D. Yeah, because in some sense, this structure has a hypertree-like structure, so basically it looks like this, and these are D linear hypertrees in here. So this is the head. So now also we apply the heuristic calculations again in this graph. Then if we remove this V, then each of these heads, the previous heads are contained in the distinct connected components. So in this case, the events that the random matching does not contain these heads are actually mutually independent. So we can apply the heuristic calculation because these events are actually mutually independent. And also, these subtrees are isomorphic to each other because of the definition of the constructions. So again, we may assume that these values are all the same. Yeah, so we can amplify. So we can apply the heuristic calculation. So it means that if we do it again, the probability that V bar is exactly same as fd, where this value, the 2 times later, this value is just a u, exactly applied to the u. So if we do it almost infinitely, then we can define some dynamical systems. So it means that if the first value was started in if the first value is started in slightly right side in here, then by these dynamic systems, it will converge to 1, and it starts to the left in then here, then it converges to almost 0 here. The only bad case is the first base case is exactly this conjectured value, but this cannot possible because it is pretty easy to show that this alpha d cannot be a rational number. It is a irrational number, but basically these probabilities are just a probability in the discrete object, so it must be a rational. So it cannot be exactly that fixed point. So we can prove that this
What if D is like power?
power to the
So, you mean the D to the minus 1 over K is irrational?
yeah, irrational.
Yeah, but sometimes it could be irrational.
I mean, yeah, but I mean, this the alpha D is not exactly d to the minus 1 okay? Just the solution of some equation,
I see.
one of the solution of the equation, and it cannot be an irrational when d is an integer.
Okay.
Yeah. Yes. So now, basically, so still we have the extendable linear hypergraph, but not exactly the regular. But it is very easy to convert it into a D regular because do it this again and adding one more edge and do the same thing. Then it convert it to the D regular. So in some sense we do this operation again. In some sense this hypergraph. Then this is our desired linear K graph. So this disproves the Kahn's conjecture.
So why does it go into beta D when you do it 2L time, or when you do an even number, when you have an even number of layers? Why does it go into beta D and to gamma D when you have an odd number of layers?
I mean, yeah. So yeah, we if this was the final function and do it again to make your D regular, then I claim that this is the V1 and this is a V2 because in this perspective, it affects very small. Very small to this probability on the V2. So in this case, this is an odd layer, and for in this point of view, this is the even layer, even the level in the hyper tree-like structure. So we can use that.
Right, but I don't understand. I'm not sure where the odd and the even coming from. You said if U is, it's like if you have.
I understand what you say. So if we start with some base case, the D regular this one, and if this probability, the head of this one, is greater than alpha D, then it's okay. But if it is smaller than alpha D, then we just update f0 as the f0. Then by the GD is the decreasing function, so this value is now greater than alpha D. Then we take this f0 again. Then we can amplify it again and again and again.
So it's,
So maybe for smaller, did you compute exactly for the smaller or those inductives?
Yeah, I mean we can compute it exactly, but it's very hard to really compute it.
I
So,
see. Yeah.
yeah.
Okay. Thank you.
So I have also one question. So if you calculate the expectation of the number of the matchings, then is it still far from the heuristic calculation, or?
No, I mean that was one of my open problem. I wrote it in the concrete remark that made it into a conjecture, but I believe that the expected size of the matchings are almost perfect, but I'm not sure that it is almost the same as to the conjectured value. But I think it is true. Yeah. But anyway, this means that the probabilities are not same for all the vertices. It can very different. Okay. So now let me talk about the second part to showing that these two values are in some sense optimal. So to do that, we need to extend the Godsil's identity to the hypergraph version. So what is the Godsil's identity? So to do that, we may define the matching polynomials. Yeah, so the matching polynomials are defined by this. So we have n vertex and k uniform hypergraph H. Then matching polynomial mkhx is defined by this number where phi is the size of the number of distinct matchings of size exactly I in H. And we also consider an empty set as a matching, so we define ph0 as 1. And the very similar concept with the matching polynomial is a matching generating polynomial. It is an n vertex and k uniform hypergraph H, which is the generating function like formula. And we have this identity. So in some sense, the matching polynomial and matching generating polynomials are equivalent because we have this nice identity. So one crucial observation is we can compute this PV bar by using the matching generating polynomials. Because the denominator QK H, 1 means is just counting all the number of matchings in H, and this number KQ H minus V1 is counting all the matchings that does not contain a V. So this ratio is exactly the PV bar. And Godsil's identity provides that to compute this this identity, we can convert our host graph into a suitable tree. So he defined this path tree that G is a graph and V is a vertex, and he defined T, G, V as a path tree where the vertices of this tree is just the passes of G, the set of all the passes of G, which is starting from V. And edges of T, we connecting two passes, P1 and P2 by an edge, if the P1 is the maximal third pass of P2. And they share the start point V. And this is the Godsil's celebrated identity. So we can, in some sense, we can convert the ratio in the matching polynomial into the path tree. And as a corollary, we have this last identity. In the graph case, we can compute this PV bar into this number where T is a path tree and this large V is the one vertex path V of G. So in some sense, to compute this probability PGV, we can convert this given host graph into a suitable tree. So we can inductively estimate this value. So this was the proof idea of the Kahn and Kim theorem on the graph case. So our aim is making this Godsil's identity into hypergraph version. So to do that, we may define the suitable notion of the hypergraph analog of the path, which I call it complete free paths, complete free works. So this definition is a bit complicated. I will explain it. So that H is a K hypergraph, and this shape is just a linear ordering of the vertices. So we just fix some arbitrary linear ordering on the vertices. Let V0 to the VL be the vertices of VH, and E1 to the EL as the edges of H, where EI containing VI minus 1 and VI. And we say that EI is the middle vertices in the EI are UI, 1 to the UI, K minus 2. And we now define a complete set CI, which is the union of the previous vertex VI minus 1 and these middle vertices Uij, where according to this linear ordering, we collect all the smaller vertices compared with then vi. Now we define a complete free work started with L and S at VL where for each I, the set EI is a disjoint from the set of all the union of the previous complete free sets. Yes. Don't worry, I will provide an example later. Okay. And anyway, this is the definition of the complete free work, and the motivation of this complete free work and the introduction of the linear ordering was the chain rule of the conditional probability. So, yeah.
So does the choice of V0 to VL is independent from the linear ordering, or?
The V1 to the VL is just for the definition. So, yeah, just the definition.
So it's difficult to visualize what this is, like from the definition. Can you?
Yeah, I prepared the example and the drawing. So, I mean, yeah, this is the example, but I will explain it a bit later. Yes. Okay, so now we have the hypergraph analog of the past for the past tree and the Godsil's identity. Now, the other thing is define the hypergraph version of past tree based on the definition of the complete free works. So we start the same situation. Let H is a K uniform, and V is some vertex, and we fix some arbitrary linear ordering on the vertices. And now we define a K work tree of H, which is rooted at V, where the vertex set of this tree, hypertree, is the set of all the complete free works that start from V. And now we will join K complete free works V0 to the V WK minus 1 as a hyper H of TH comma V, where I will do it. So, let's say this W0 is some complete free work. Now we will make it into a hyper H, candidate hyper H, where each Wi is obtained from W0 by adding a some edge E prime, where E prime is L comma U1 to the U K minus 1, and obviously, and again, of course, this EI is disjoint from the complete free set of the W0, complete set of the W0, and WI is W0 and EI and UI. Then the choice of this, the subscript I is obviously exactly K minus 1, so this is a hyperpage. And this definition of the complete free works and the K work trees are, if K is a 2, then these definitions are exactly the same as the past and the past tree.
So your choice of E prime is same for the every W1 to W2.
Yes.
And only
This is the same, but we need to, but the definition of the complete free work, we need to, fix the last vertices.
Yes.
But the possible way to fix the last vertex is exactly K minus 1, so we have a K uniform H. And it is pretty easy to show that this, according to this definition, this K work tree is actually the hyper tree. Okay. So, and I will skip this. And if you prove some very nicely, then we can prove this corollary. The P V bar is exactly the same as the PT large V. So this is the hypergraph analog of the Godsil's identity. So by using this corollary, we can prove that our second theorem, the probability of that the PV lies between the two numbers, the beta D and gamma D. Okay, so now I will explain the example. So for the convenience, let H be the tetrahedron, the 3 uniform hypergraph with which is a click on the 4 vertices, and I will give a natural linear ordering 1, 2, 3, 4 in here. And now we will construct the K work tree based on the complete free works, and we will fix the vertex 1. So this vertex is just one vertex work, and the first case is we may extend 1, 2, 3 and 1, 3, 2, which is edges 1, 2, 4, 1, 4, 2, you know. And now in here, if you extend this vertex into some other edges, so that we need to check what is the complete set for in here. But in here, the complete set is 1 and 2, because the definition of the complete free work, 1 is contained in the complete set, and this 2 is smaller than 3 in the linear ordering, so this 2 is forbidden. So we cannot use 1 and 2. So if you want to extend it into some other edge, then we need to find an edge which is incident to 3, but not containing 1 and 2. But it's impossible. So this cannot be extended in here. But in here, 1, 3, 2, this 1 is in the complete set, but 3 is greater than 2. So 3 is not contained in the complete set. So we can use 2, 3, 4, and we have a edge 2, 3, 4. So we can extend this, this complete free works in here. So we apply all the cases, then we obtain this hypertree. And this is true because now let's see that. Let's check that this equality holds. So in the first case, let's compute the P1 bar. So the number of matchings in H is exactly 5, the empty set and each edge is 4 edges. So we have 5 distinct edges, distinct matchings. And the number of matchings which does not cover a vertex V is exactly 2. Just an empty set and the edge 2, 3, 4. So the probability that P1 bar is 2 or 5 in this tetrahedron. Now let's check that the probability that the random matching does not cover this 1 is same as 2 or 5. So now the first let's compute that the number of matchings which does not containing this 1. And it does not contain 1, then it is just disjoint 3 edges. So the number of matchings in these 3 edges are 2, 3, 3, so 8. Now assume we containing a vertex V, a vertex 1 is in the matching, and we may assume that this 1 is covered by this edge in here. Then we cannot use this, cannot use this, but we can use these 2 edges. So we have 4 matchings, but the number of possibilities that choosing these edges are 3. So we have additional 12 edges. So in total we have 20 edges, 20 matchings, but the number of matchings does not cover this 1 is exactly 8. So the probability is 2 or 5. So this equality holds. So now I will put some. I want to share some open problems related to this work. So basically, the construction uses the limit of the dynamical systems. So it relies on the fact that we can fix D as a constant. So we can amplify the number of vertices as much as we can do. So maybe the number of vertices in the counter example equals a lot of vertices. But what if we consider the D is in some sense polynomial in the number of vertices? So what if the D is also grows with the number of vertices? So the conjecture is when K is at least 3 and H is n vertex, K uniform hypergraph, and these hypergraphs are almost regular, where D is at least n to the epsilon, so polynomial in n, and also this is bounded by the co-degree is in some sense very small, and still CAST conjecture is true. So I mean, I don't think I mean, for me, I think this is 50-50 for me. So I'm not sure this is true, or I'm also not sure that there is a counter example. But why I dispose as an open problem? Because if this conjecture is true, then we still have lots of interesting consequences. For example, if this conjecture is true, then every Latin squares has the almost same size of the partial transposers, which is very hardly dependent on its specific structures. And also we can apply this to the average size of the partial designs in various parameters. And also it seems also there are lots of consequences on especially the design theory and also some embedding problems. Yeah, so I pose this conjecture, and if this is true, then it has lots of interesting consequences, I think. And I want to close my talk with introducing this another conjecture of Kahn, which is very highly related to my work. So let H is a K-bounded. The K-bounded means that every edges are contained at most K vertices. And this is a still linear hypergraph with minimum degree goes to infinity. Yeah, so in some sense these H are the sequence of the hypergraphs. And now we consider two edges, A and B, two edges, and their distance between A and B is also goes to infinity. Then this is true. The probability that random matching containing both A and B is asymptotically same to the probability that the A is contained and times the probability that B is contained in the random matching. So it means that the event that the edge containment in the random matching are in some sense almost independent or not. So if we divide this number PA in these two, then we can make it into the conditional probability and just P, B, and M. And since its minimum degree goes to infinity and distance is far from goes to infinity, their distance. So in some sense, if we convert this problem into the K work tree that I just introduced, then these two K work tree shares some similar structures in some sense. So maybe we can prove this by using the K work tree that I introduced, but yeah, I couldn't prove this. But anyway, I think this is very interesting conjecture.
Prove? Just prove?
Yeah, just prove. I think this is true. I believe this is true. And yeah, and again, this is proof when we restrict this conjecture onto the graph, then it is true. Okay, so yeah, that's it. So thanks for
Thank you. Any questions?
Your main theorem was you found the both vertices V1, V2 simultaneously, right?
yeah,
So I just confused.
just in the same hypergraph.
Just saying that. So using the conflict free then.
No, that was for proving the probabilities are in some sense optimal. So.
can you say, like, I mean, your example is you have one vertex, when you delete it, break graph is completely disconnected.
Yeah.
And you have many components. I mean, not many, but.
Yeah. it's
So, if we assume that hypergraph is like too connected, like removing one vertex will never leave the disconnected graph for a hypergraph, then is there a chance that Kahn's conjecture could be true, or still there could be a counterexample?
I mean, I don't know because when I visited the Heidelberg University to give a talk in here, I discussed with several related problems to that group. One posed that if we consider the random hypergraph, which is obviously maybe too connected, then still then whether the Kahn's conjecture is still true or not, but we couldn't make any progress on that, so I don't know.
So is there like easy way to modify your example so that the connectivity could go up?
I mean, I'm not sure, but I think there is some way to adding the connectivity condition. So our hypergraph is highly connected, but Kahn's conjecture is not true. I think. Yeah. I never tried that direction. So.
Any other questions? How did you start this project?
I read the Kahn and Kim's conjecture on the airplane when I go to the Hamburg. because some students just suggested me, just recommended that if you don't have something to do on the airplane, then just read the paper, some articles. So I choose the Kahn and Kim's paper, and I just saw this conjecture, and it seems I can make a progress on the conjecture. So yeah.
Alright. Okay, if there's no further questions, let's thank the speaker.